But if you only have one enemy, you're that's kind of okay. All right. Does anyone have excuse me? Does anyone have questions about the exam before we dive in? What was question 6? Oh, so it is. So I basically tried to give you guys a little bit of a head start on there. 1.015 centimeters cubed, right? So I was basically giving you the volume of the cube of silver. Agreed? So what's my second conversion? Right, so density, right? So I want to get rid of the centimeters cubed. I have 10.49 grams per centimeters cubed. Now I have grams. What's my next one? I can go to moles per gram, right? So 1 mole per 107.87 grams. Some of you chose 197 grams for silver. And so it makes me think that you guys decided that gold was the same thing as silver.
Yeah.
Everyone in here has seen AgNO3, right?
Yeah.
It's silver nitrate. Gold nitrate is not cheap, as far as I'm concerned. So a couple of you actually chose 197, and then you just have 6.022 times 10 to the 23rd atoms of silver per mole, right? Some of you combined the last two steps, and you ended up with 6.022 times 10 to the 23rd atoms per 107.87 grams, which was fine. You ended up with like basically slightly more than a mole's worth of atoms. Agreed? All right, so the only thing on this, the only part of this exam that I expected to be like mildly tricky was number 6, part B, right? So number 6, part B is actually not bad, and it's one of those problems that is so simple that you kick yourself for, right? So if you look at this, you now have the volume of a cube. Agreed? You have the total number of atoms. Agreed? You have the volume of the cube that is occupied by atoms. Agreed? You have those three things. So how can you get the volume of a single silver atom? Right, so I would take my, this is actually terrible, and you guys are gonna dislike me for how easy this is. It's one of these situations. The volume of your cube was something on the order of 1.0456 centimeters cubed. Agreed? All right, so if I multiply that by 0.74, that's volume of silver atoms. Agreed? What's my total volume of silver atoms? Right? And then if I divide this number by the number of silver atoms from the previous question, I get volume per atom. And that's it. So I tried to set you guys up for that, right? I was like, hey, 74% is filled with silver atoms. Calculate the volume of a single silver atom. It was this really, really easy thing, but I also expected this to be like the most mildly tricky on the entire exam. At the same time, I only made it worth 6 points. And I think I gave everyone partial credit for trying. People threw out like volume of a sphere, volume of a cube. They tried to isolate R's, and I'm like, cool, half credit. But deceptively simple. Anything else? Can I point something out to you guys that a couple people missed? So on number 8, there's an electron affinity for oxygen for 2 electrons. And we had a problem like this on the board what do you guys notice about the value of that electron affinity? Is it positive or negative? It's positive. A lot of people in here assigned a negative value to it. Now, why is it positive? We had a couple examples like this. Why is it positive? What would the first electron going into oxygen be? The first electron going into oxygen would be negative or positive? The first electron would probably be negative, right?
What do you mean by the first electron?
So this is cramming 2 electrons into oxygen, right? Right. So it says for 2 electrons. So oxygen by itself, you know, is sitting right here. It's S2P2 instead of S2P4. It wants to be a noble gas. The first electron would be negative, right? There's a negative energy associated with that, right? It gives energy away when it accepts the first electron. What about when it accepts the second? Right, the second is going to be increasingly positive because you already have 9 electrons that are stabilized by 8 protons. What happens when you add the second one? You have to pour a bunch of energy into it because you basically have 10 electrons stabilized by 8 protons. It's a difficult system. And so a handful of you caught it. You caught that it was positive and you had it on the left. A lot of you flipped the sign to negative and stuck it on the right-hand side. Now, these are all negative, right? Chlorine, chlorine, bromine, iodine. These give off energy, so they would be on the right-hand side. For 2 electrons, these guys are going to be positive values to get to be a noble gas. All right. Are you guys ready to start chromatography? Awesome. Let's start chromatography. So what's really nice is that you guys have all done the ferrocene lab. You've completed it. You did a column. So this should all be kind of, you use that as intuition for this entire lecture, right? So I like this sweatshirt chromatography. If you spill something on your shirt and you're kind of having like a sweaty day, it like moves up the shirt in different layers, right? If you have a hamburger stain, right, it would eventually separate into top bun, employee spit, pickle, meat, bottom bun. It's wonderful. Right. So chromatography is a separation based on different interactions of compounds with 2 phases. There is a mobile phase and a stationary phase. And effectively, the mobile phase moves through the stationary phase, right? So this is the solvent that flows through the supporting medium. The stationary phase is effectively your silica beads or a layer or coating on the supporting medium that interacts with the analytes. The supporting medium is a solid surface on which the stationary phase is bound or coated. So this can be either silica, or this can be the silica with a C18 chain on top of it, like a non-polar C18. And this is some combination of 1 or more solvents. All right. So, for example, if you had a column, you would have a combination of materials, right? And as you push solvent through, they would begin to separate and begin to separate and then fully separate. And you would have a detector signal and then peaks come out in which you can separate and then collect your individual components based on the injection mixture. So we have a couple main types, right? We have liquid chromatography, which the mobile phase is liquid. We have gas chromatography, in which the mobile phase is gas. And then we have supercritical fluid chromatography, which is very fancy and is not done a whole lot in academic centers. So liquid, liquid or partition, liquid bonded phase, liquid solid or absorption, ion exchange. So this is typically TLC. Do you guys know what I mean when I say TLC? You're shaking your head yes, Elizabeth. You get to answer. What is TLC? What does the TLC stand for? Thin layer chromatography, right? Thin layer. So did you guys do that in organics? Lots of head shaking yes. Good, good. Ion exchange and then size exclusion, right? So this is liquid typically absorbed on a solid, organic species bonded to a solid, just a solid in general. The type of equilibrium is just absorption to the solid itself. But then your mobile phase moves up and it carries the components that you're separating with it. I'm not going to just very slowly read through this entire chart. Just wanted to touch on it. All right. So we have two main types of chromatography. We have gas chromatography and liquid chromatography. You guys never would have expected this, but gas chromatography uses gases. Liquid chromatography uses liquids. All right, so there are different types of methods, right? Gas solid chromatography, gas liquid chromatography. This is not used as much. Bonded phase gas chromatography, there's a chemically derived support system, but what you effectively have is a gas chamber, right? A flow controller. You inject your sample in, it goes through this column that is so much obscenely longer than this, that is ridiculous, and then it comes out and hits a detector. Good so far? This is really, really low-hanging fruit on the chemistry joke tree. All right, so I think that you guys, it doesn't do me any good to sit here and read slides. I think it would be better if I kind of just started talking about my discussions here, or started talking about graphics. So a lot of times you would have what is effectively a column, right? And so the column is actually only about this big, right? It's this little tube this big, and it's packed with these extremely small silica beads. The silica beads have all these little tiny channels in them, right? And so what will happen is there is effectively a flow pathway, and that's which my solvent kind of comes through and comes through and comes through and comes through and then comes out, right? And so it is going through all this silica and all these different pathways, and the surface of the silica is interacting with my analyte in different quantities. The more that it interacts, what happens to its path? Right? If it's not interacting at all, it's just like, woo, out. It goes through really, really quickly, right? So that would be component one, right? This would go through the absolute quickest. This would have a small amount of retention, right? These would have the largest amount of retention, and you would have peak convolution in which they're not fully separated. If you are a chromatography person, you can get a job thrown at you in a second, because there's a lot of separations and quality control labs that they just want you to run their sample, tell them that it's good, tell them that it's bad, and you can get paid right at 6 figures doing that for a lab company. I got offered a job this morning to manage a toxicology group, basically doing a lot of this for biological samples for hospitals, for just test labs. And I declined. I told them that I like doing science, not managing other people doing science. But it's interesting, right? Because it's all the same stuff. All right, so you have two different types of columns. You would have a packed column or an open or tubular capillary column, right? So this is what you actually get the most. A column is packed with these silica beads, and these are exaggerated in size, right? So what is the best packing efficiency this can probably have based on what you guys know about packing efficiency? This is about the best that this can possibly have is 74%, right? That's as good as it gets. So that means that I can still have liquid flow through here relatively easily if I apply enough pressure based on my 24% empty space, right? All right, so an open or tubular capillary would have some porous layer on the outside of the tube, or it would have a wall-coated open tube. These aren't seen quite as much. This is pretty much standard chemistry separations.
How would those be affected?
So these would effectively happen over very, very, very long distances that do not require aggressive separations. And then there are flow profiles in which if you have a tube, you would have a laminar flow, right? And so a laminar flow is when you have basically a plug of liquid moving like this, right? And so what's happening is you constantly have this churning of liquid twisting to the outside in order to push the flow through the tube such that all liquid is eventually exposed to this outside diameter in this three-dimensional rate. So you would have laminar plug and tubular plug flow, but this is like an advanced separations class. This is not appropriate for this. Okay. This is an example of TLC, right? You would have had your spotting plate right here. You would have had your solvent line. It would have carried up, right? And then you would have had this traveling to here and your other component traveling to right here, and then separation of your mixture from the beginning. Okay, so there's a typical response obtained by chromatography, concentration versus elution time, right? So if you have an injection, right, and then you basically like start your run, inject, go back, you would have this TM, which is a void time, right? And then you would have the length of time coming out, which would be your retention time of your analyte that is retained in the actual column. And then the way to actually measure these is baseline width of the peak in time units, and then half height width of the peak in time units. You use these calculations to determine peak area, which tells you a little bit about your analyte and how it was behaving in the column. All right. So we can have a difference in retention of the solutes, and this is effectively the same thing as, do you guys remember what you calculated for TLC? Yeah, this is the same thing as RF value, right? Your retention factors. So a difference in retention of the solutes, right? And then a sufficiently narrow width of the solute peaks, which means that there's good efficiency for the separation system. So this would be a significant width for them to be separated, right? As long as it can return to baseline. So peak width and peak position both determine separations of possible peaks. If this excites you, there is job after job after job waiting for you that pays well. There are so many labs that want you running their LCs, their GCs, replacing columns. All right, so let's do a little bit of math. It's actually pretty straightforward. A solute's retention time or retention volume in chromatography is directly related to the strength of the solute's interaction with the mobile and stationary phases. It's a mouthful, but it kind of makes sense. Retention on a given column pertain to the particulars of the system. It depends on the size of the column, right? If your column is like 10 meters long, and GC columns get ridiculously long. LCs are like this big, right? GCs you can stretch across the room a couple times. And then the flow rate of the mobile phase, The average migration rate, which is this V bar, is L over TR, right? So the length over the retention time. A more universal measure of retention determined from TR over VR is going to be either of these two equations. I kind of wanted to tell you guys that this isn't something that I care a lot about in this class, right? What do you guys think that I probably am going to emphasize in any amount of chromatography on the final? What would be your guess? Yeah, I would want concept, right? And then I would look for, is this sufficiently separated or not? Yes, right? If it was not separated, what could you possibly do to the chromatograph instrument to separate it? We're not there yet, but I want this to be like concept based. All right. The value of the capacity factor is, again, K prime. This is moles of stationary phase per moles of mobile phase, right? This is related to the strength of the interaction between a solute with the stationary and the mobile phases. When the K prime is about 1, the separation is really, really poor. When the K prime is greater than 30, what is that telling you? That means that the column is holding on to the analyte too aggressively, right? It's not actually going to come out. When the K prime is about 2 to 10, you can get this weird perfect balance of holding on to the solute just enough and allowing them to come out in a reasonable time frame. All right. A simple example relating to K prime to the interaction of a solute and column is illustrated for partition chromatography. So A in a mobile phase, and does anyone know what KD is? You guys are like whispering it. It's a dissociation constant. That is perfect. Talk to me about a dissociation constant. Why are we dissociating? Why are we dissociating? Right, my analyte is moving through the column. It comes upon some of the stationary phase that it's attracted to. It forms some hydrogen bonds, right? And then what is the dissociation part of that? It kicks off and then continues down the column, right? And so you're going to have mobile phase, dissociation constant, stationary phase. And it's going to constantly, your analyte is going to constantly shuffle back and forth between those two, right? So your KD is your equilibrium constant for distribution of A, right? Your analyte between the mobile phase and the stationary phase. You can go into these calculations. I don't think that you guys need these right offhand. As KD increases, the interaction of the solute with the stationary phase becomes more favorable, and the solute's retention, K prime, increases. Right, so that means that the column is going to hold on to it more and more and more, and it's going to be a peak that comes out later. All right. So if I were to have two different analytes, A and B, separation between the solutes requires different KDs for the interactions with the mobile and stationary phase. You can determine free energy based on the different KDs. Peak separation will also represent different changes in free energy, which that's what you would expect, right? No two molecules are the same, and if they are, they're the same molecule, right? Therefore, everything that is different is going to have a slightly different KD. It just has to be different enough to show up as separate peaks. All right. Efficiency is related experimentally to a solute's peak width. An efficient system will produce very, very narrow peaks. Narrow peaks go to a smaller difference in interaction in order to separate two solutes. Efficiency is related theoretically to the various kinetic processes that are involved in this. So you can determine the width or standard deviation of the peaks, right? So we have this WB is 4 sigma, right? You can estimate sigma from the peak widths. And then WH is 2.354 sigma, right? Such that we can assign that of the individual peaks. So I kind of want to talk about problems really quickly before we get into this, because we haven't troubleshot anything. So there's middle territory, right? If I have if you're basically running a separation, right, and you have some compound that you're trying to separate, and you'll say you have 3 different compounds and you're trying to get them into 3 individual peaks, and you collect the peaks by hand. If you inject the smallest amount of material possible, then you would end up with peaks that look like these little tiny guys. Would this be an effective separation? Do you have any peak convolution? Or any of the peaks overlapping each other? No. Did you isolate a lot of pure product in your separation? No, not at all. Let's say that you inject a very, very large amount. You're like, look, I've got things to do today. I do not want to sit here and just run columns over and over and over again. You are effectively going to saturate and you get something that looks like this. You guys want to talk to me?
Those 2 peaks are blended together.
So, and you don't know that, right? You can't tell. Your detector is so this line represents the maximum amount of signal that can be picked out, right? You've saturated your detector, right? You've injected this large amount because you're not going to sit there and you take your time. You're like, cool, I separated this. I have this peak. I have this peak. There is obviously more of this one than there was of this one. Separated. I'm done. I'm out. What are your thoughts on this? Do you guys see how someone can kind of like rush through that? I'm going to do 5 different separations in one run, right? So where's the middle territory? Where's the healthiest middle territory that you can possibly have? Sarah, your hand went up.
So are you saying that the objective is to get like as specific as a small peak?
Well, to be able to distinguish between them because what you're doing is this is dropping out of a line and you're like catching it in a vial the same way you guys did with your column for ferrocene, right? So you have 3 different subjects here, right? 3 different analytes that are coming out of the end of a tube. Your detector is telling you there's a signal, so you should collect. So I have to do 2 different things. This one's good, right? I have clear peak separation. This, the best that I can possibly get away with is some clear peak separation between the 2. I have to have peak separation to where my detector goes back down to a 0 peak before it comes back up, and I can collect individual ones. Now, I have a question for you guys. Conceptually, how can I make these peaks come out sooner or come out later? This is a multivariable system, right? The way that I've drawn it right now is Bob just got really lazy and ejected his entire sample into the LC. Yeah. So temperature for what system? Not LC, but GC. So you do a temperature gradient for GC. Now, how would you change the temperature if you wanted them to come out if you wanted a longer retention time. That is awesome. You would cool the system or you would decrease the temperature ramp. And what is going to happen as you decrease the temperature ramp is this entire thing is going to spread out. But what is that also doing? It is increasing the amount of time that you are sitting in front of the computer staring at the screen. Is that okay for me to argue as well? You would have something that looks like this. Then can you dump in a whole lot of sample? You can absolutely dump that in. Is it worth it if it takes twice as long if you did 5 GC runs at once? Yeah. All right. Awesome. Does this make sense so far? Are you guys okay with me like drawing these graphs and discussing how to manipulate them? Because I think that this has a lot more value than these guys. All right. You just dump in a larger amount of sample. So your injection volume and your injection concentration.
How would you want to put as much as you're going to, why would you want to put that much?
For my PhD, I ran a protein carousel for 5 years, and it would generate about 5 grams of protein every 3 or 4 days, which is a lot, right? That's actually a lot of a very, very specific protein, and it built it amino acid at a time, right? And so that means that the day after, I would have to purify all 5 grams of that specific protein on an LC, right? And so that means that I could either inject it 500 microliters at a time, or I could adjust this to inject 5 milliliters at a time. Does that make sense? And so I could do it in 10 hours of runs, right? Just very, very small amounts of these little baby peaks, and I'm collecting them, or I could do it in 4 runs. That would take me an hour and a half. And then I could work on NMR or doing Stille couplings. Because you'll get this like very, very crude material that has all these byproducts, and you want just your pure protein. When you isolate, you know that is one peak. For me, it was at exactly 16.2 minutes in my run, right? I had this big fat injection peak that I would collect here and I would rerun. I had a side product peak here and a side product peak out here, but I knew exactly how much I could inject because I had adjusted my run to do this ridiculous 5 mil injection, and I had set my peak times to separate in between. Does that make sense? All right, so this is for GC, right? We've adjusted GC. So if you had these peaks that were already really, really wonderfully separated, all right, let's draw another column out here. I have these peaks that are wonderfully separated. They're nowhere close to each other. But it takes 22 minutes for that last peak to come out. Which means that you have to purge for 5 to 10 minutes. After this, reset, you get about 1 run every 40 minutes. Right? So what can I do to make my life better? Not increase temperature, increase my temperature ramp. Right? What do I mean by ramp? It's just degrees per minute. Right? And so what is going to happen is this entire thing is going to speed up. So if I was like 20 degrees per minute, I might jump to 30 degrees per minute, and all of my peaks are going to come together. And come out much sooner. Does this make sense?
Wait, so clarify the ramp, you're saying it will increase like 33 degrees per minute?
So if I was at like 10 degrees per minute, right, I've jumped to like 20 degrees per minute, which means that I'm getting hotter faster. And then what happens to kinetics as a function of temperature? They speed up, right? So what is happening in my association-dissociation mechanisms? It's dissociating faster, which means it's moving through the column faster, which means it's coming out at an earlier time. Does this make sense? Now, what does temperature only work for? It only works for GC. What are my gases typically in GC? Does anyone know offhand? We typically have helium, there's some N2, right? Nitrogen, they're very, very benign, non-interacting gases, right? So the only thing that they're doing is they're creating a flow down the column to effectively push the analytes out, and they are associating and dissociating with the column more or less as a function of temperature. Are we okay? Is this better than the PowerPoint lecture and just pointing at things? Awesome. I think that this actually makes a lot more sense. All right, so we've talked about injection height, we've talked about peak convolution, peak deconvolution, we've talked about moving the peaks faster, we've talked about spreading the peaks out. Are we good so far? This is just for GC. Right. Let's talk about LC. So talk to me about LC. What's going on? Does anyone want to talk to me about my stationary phase? Does anyone want to talk to me about my mobile phase? What is the liquid? Does anyone know what options are? So hexane would be for, that's for a normal phase. And there's normal phase and there's reverse phase. I haven't talked to you guys about that yet, but that's wonderful. So your reverse phase, LC, is when you have this C18 packed column. And so does anyone know what I mean when I say C18? 18 carbons in a chain, right? And they're all just saturated with hydrogens. So it's basically greasy. It's a non-polar coated silica. So if this is non-polar, what am I going to push through it? I'm going to push water through it. Are we okay? No, the C18 is the stationary phase. I basically have these silica beads. This is actually the standard for most liquid chromatography. On the surface of these beads, I have these C18 chains, and it's just non-polar interactions for molecules to basically get away from water and stop interacting with that. So you have this column that is effectively full of these beads. They're all full of C18s. Right? I have water as my main solvent pushing through. Are we okay? So what is typically going to come out first? What's going to come out first in a water C18 stationary phase liquid chromatogram? Bam, that is awesome. So the first thing that's going to come out is most polar, right? Why most polar?
Goes through the non-polar.
Well, it doesn't interact, right? It doesn't interact with this very much. What is it interacting the most with? The water phase. Therefore, it is going to blow through this column the absolute most quickly possible, come out, and you're going to have your most polar molecules. Now, what happens? You have something that's just hiding in these C18 chains on the silica, and it wants absolutely nothing to do with water. Well, but last is like 3 hours, right? So let's say you have some like, what are mothballs? Anthracene. Mothballs are like, what are these structures? Well, they're like multiple benzene rings. They have no polar components at all. This would effectively hide in here forever, right? And so you're just staring at this for hours and hours. You're like, God, come out of there. Sweet baby Jesus, get out of this column. I got to do another run. Otherwise, you're eventually going to build up a whole bunch of stuff in your column. So what can you do to your mobile phase? You can't just increase flow, right? If you start increasing the pressure, you're just going to break the end of this open and just shoot silica beads out the end of it. What can you do? You can add something to it that's less polar. And that's wonderful. That is an absolutely wonderful thought. So does anyone have suggestions? Right, we have our mobile phase. Our mobile phase is water. The only way we can make that more polar would be to add methanol to it. Right, but what can we do to make it less polar? What is miscible with water? I don't expect anyone to know this offhand. Does anyone know? Have you guys ever heard of a water acetonitrile blend? So acetonitrile, and whenever the news gets a hold of this, they like to call it methyl cyanide, right? Because it makes people's eyes get really, oh my God, methyl cyanide. That sounds dangerous. You can touch it, spill it on your hands, take a bath in it. This is really non-polar, but it still blends with water. So if we wanted a very, very normal runtime, right, and we wanted to push everything out of our column that was non-polar, what could we do? And we can change the percentages as a function of time. Yeah, so we can start with a 100-0 start time, right? And then we can say, all right, I want 5% per minute all the way up to 0 to 100. I want 0% water, 100% acetonitrile. What is going to happen when you start pushing 100% acetonitrile through the column? What am I going to do? I'm increasing my interactions with these guys, and I'm effectively cleaning out everything. Is this okay? Does this make sense? Now, someone mentioned hexanes earlier. And that is not a bad mention in any way whatsoever. In what way would hexanes be appropriate? Would hexanes be appropriate with a C18 column? No, why not? They're both non-polar. This is wonderful. You have to have competing intermolecular interactions, right? Competing intermolecular forces. So if you were to use hexane as your mobile phase, what would that need to mean about your stationary phase? Your stationary phase would need to be polar. This is wonderful, right? So that would mean that if I have just a silica bead, what is the surface of the silica bead itself? Has anyone ever seen capillary action on glass surface? Right, so that means that on the surface, you have oxygen, 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 and they'll actually have hydrogens on the end of them, right? So polar molecules will come in and dock into these hydrogens, and that is your association to your solid support, which would mean that you would have to have, say, hexane running by. What could you blend into hexane that is miscible with it? Is water miscible with hexane? I got a couple head shakes. No, that's awesome. How can we increase the polarity of our mobile phase to then pull our analytes off of our polar stationary phase? Yeah. Yes, that's it. Yeah, because ethanol is miscible with hexane, right? Methanol is miscible with hexane. Are those very polar? Yeah, they hydrogen bond, and so you can just do a blend ethanol, methanol, whatever you need, and then eventually at the very end, you would have this 100% ethanol methanol purge, cleaning everything off of your column. When you have a really long retention time, if you have like a bunch of peaks down here.
I thought you said hexane wasn't.
No, it is. It doesn't work with reverse phase. It doesn't work with non-polar supported stationary phase,
Okay.
right? Because then you have a non-polar mobile phase and a non-polar stationary phase, and you don't have, you're not shuffling your intermolecular forces back and forth.
Oh, wait, so hexane's the stationary thing?
No, hexane's your mobile phase. Your stationary phase is always your silica, and there's either nothing on the silica and it's polar, or there's a C18 on the silica and it's nonpolar. Now, what else can you do to your silica beads? You can stick antibodies on them. You can grab anything. You can have size exclusion. You can have molecule specific ligand catching molecules on there. What's the word that I'm looking for? You can have monodentate, bidentate, metal specific components functionalized on your silica. You can basically make chromatography specific to anything that you want to separate. Does anyone know the name Keith Panel? Shut the door for a second. Does anyone know Mike Panel? That was here a couple years ago. I'm going to turn off the recording feature for a second.